Welcome to today's problem walkthrough. In this session, we'll explore problem number 723, Candy Crush, a fascinating scenario inspired by the popular game. We'll delve into how to identify and remove matched groups of candies and repeat the process until the board stabilizes. Let's dive in. In this problem, we're working with a grid that simulates a Candy Crush game. The grid is represented by a 2D array called board, where each cell contains a positive integer representing a candy type, and a value of 0 represents an empty space. The goal is to simulate the Candy Crush game until the board stabilizes, meaning no more candies can be crushed. A candy gets crushed when 3 or more of the same type are adjacent, either horizontally, vertically, or both. Once candies are crushed, the affected cells turn into empty spaces, and any candies above them fall down to fill the gaps. This process is repeated until no further crushing is possible. The task is to return the final state of the board after all crushing operations have been completed. Now, let's look at an example to understand the process better. Suppose we have the following input board. Each number in the grid represents a specific type of candy. For instance, the top left corner contains candy type 110, followed by candy type 5, and so on. The board has 10 rows and 5 columns. Remember, our job is to repeatedly identify and crush candies that form groups of 3 or more, and then allow the remaining candies to drop into place until the board stabilizes. This board layout will help us visualize how the process unfolds. After performing the Candy Crush operations, the output board looks like this. Notice that several rows have become entirely empty, as the candies in those rows were crushed. For example, candies forming horizontal groups like 5, 5, 5, and vertical groups like 2, 2, 2 were identified and removed. Once these candies were crushed, any candies above them dropped down into the empty spaces. The process continued until no more groups of 3 or more candies were found. The result is a stable board configuration where no further crushing is possible. In this example, the crushing process involves both horizontal and vertical groups. For instance, a horizontal group of 2, 2, 2, 2, and a vertical group of 2, 2, 2 were identified and crushed. After each crushing step, candies above the empty spaces fell down to fill the gaps. This cycle repeated until the board reached a stable state. The final board shows the result after all operations, where no further groups of 3 or more adjacent candies can be found. Now, consider another example where the input board consists of distinct candy types, as shown here. Since there are no groups of 3 or more adjacent candies of the same type, no candies are crushed, and the board remains unchanged. The constraints for this problem ensure that the board dimensions are between 3 by 3 and 50 by 50, with candy values ranging from 1 to 2000. Edge cases to keep in mind include boards with no candies to crush, boards with all candies of the same type, and larger boards requiring multiple crushing iterations. These scenarios help you understand the range of inputs and outputs you might encounter. Here, we start by considering the brute force approach, which is a straightforward way to solve the problem. The idea is to repeatedly scan the board, identify groups of 3 or more matching candies in a row or column, and mark those candies for removal by setting their values to 0. Once the candies are marked, we collapse the board by shifting all non-zero values downward, filling the empty spaces with zeros. This process is repeated until no more candies can be crushed. While this method is intuitive and simple, it comes with a high time complexity of O, open parenthesis m times n close parenthesis squared, since we have to traverse the board multiple times during each iteration. However, it uses space efficiently with O(1) space complexity, as all operations are performed in place. The brute force approach, while functional, has significant drawbacks when applied to larger boards. The main issue is inefficiency, as it requires a full traversal of the board during every iteration, even in regions that remain unchanged. To address this, the optimized approach builds on the brute force method but improves efficiency by focusing only on areas of the board that were modified during the previous iteration. For example, candies can only be crushed in rows or columns that were affected in the last step, and collapsing the board impacts elements only within the same column. By leveraging these observations, we reduce redundant operations. The key steps involve marking candies for removal using an auxiliary structure, collapsing the board by shifting non-zero elements downward, and repeating the process, but limiting rescans to affected rows and columns. This approach has a better time complexity of O, k m*n, where k is the number of iterations, and it still maintains an in-place space complexity of O(1). The optimized approach offers clear advantages, especially for larger boards. By narrowing our focus to only the rows and columns that were modified in the previous step, we significantly reduce the number of unnecessary checks and iterations. This targeted strategy allows the board to stabilize more quickly, making the algorithm faster and more scalable. When comparing the two strategies, the optimized approach was chosen because it strikes a balance between simplicity and efficiency. While the brute force method is easier to implement, it becomes impractical for larger boards due to the repeated full traversals. The optimized approach, on the other hand, retains much of the simplicity of the brute force method but operates significantly faster, particularly when changes are localized. The key insight, or aha moment, was realizing that changes propagate locally, enabling us to improve performance dramatically without adding much complexity. Ultimately, the optimized approach was selected as the final strategy due to its superior balance of simplicity and performance. It avoids the inefficiencies of the brute force method while still being straightforward to implement. By focusing on localized changes and minimizing redundant rescans, the algorithm achieves better scalability, making it the most practical solution for this problem. This choice ensures that the solution is both efficient and adaptable to larger board sizes, fulfilling the requirements of the problem effectively. In this problem, we are tasked with simulating a simplified Candy Crush game on a 2D board. Each cell in the board contains an integer, which represents a specific type of candy. The objective is to repeatedly identify and remove groups of 3 or more adjacent candies of the same type, setting their positions on the board to 0. Once these candies are removed, the board collapses by shifting non-zero values downward, filling the empty spaces. This process continues until there are no more groups of candies that can be crushed. We start by initializing the board, which is given as an m by n grid, and we define a variable called change to monitor whether any candies were crushed during the current iteration. Initially, changed is set to true, so we can begin the iterative process. The algorithm is designed to run repeatedly while the board remains unstable, meaning that candies are still being crushed in each iteration. To simulate the Candy Crush mechanism, the first step within each iteration is to detect all candies that need to be crushed. We traverse the entire board, inspecting each position one by one. For every candy at position I, j, we check horizontally to see if there are at least 3 consecutive candies of the same type, and then perform the same check vertically. Any positions meeting this condition are marked for removal, using either a set or a 2D Boolean array to track them. If no candies are marked for crushing during this step, we set change to false, signaling that the board is now stable. Otherwise, we move on to the crushing step. Here, all positions in the board that were marked in the crush set or array are cleared, meaning their values are set to 0. After crushing, we collapse the board column by column. For each column, we extract all the non-zero values and store them in a temporary list. These values are then placed at the bottom of the column, and any remaining positions at the top are filled with zeros. This ensures that the board reflects the updated state after the candies have fallen into place. This algorithm hinges on several key insights to ensure efficiency and correctness. First, detecting groups of candies to crush requires scanning the board both horizontally and vertically. By doing this in a single traversal, the time complexity for detection is optimized to O, m*n, per iteration, where m and n represent the dimensions of the board. Second, the collapse operation focuses on individual columns, efficiently moving non-zero values downward. Using a temporary list to handle this makes the implementation straightforward and avoids unnecessary complexity. Finally, the concept of a stable state is critical. By tracking whether any candies were crushed in the current iteration with the changed variable, we can terminate the process as soon as no further crushing is possible. The data structures play an important role here. The board itself is a 2D list that is updated in place, while the set or Boolean array used for marking positions ensures that detecting and clearing candies is both simple and efficient. Analyzing this algorithm reveals important details about its performance. The time complexity is primarily determined by the iterative process. Each iteration involves a full traversal of the board for detecting candies to crush, which is O, m*n, followed by collapsing the board column by column, which is O, m, for each column. Since there are n columns, the collapse step is also O, m*n, per iteration. In the worst case, the number of iterations is proportional to the number of rows, m, yielding an overall time complexity of O, m²*n. The space complexity is dominated by the storage required for the crush array or set, which is O, m*n, in addition to the board itself. Beyond performance, the algorithm also addresses several edge cases. For small board sizes, such as 1x1 or 1xn grids, the logic must handle these dimensions gracefully. If no candies are crushable, the algorithm should terminate cleanly without unnecessary processing. Handling multiple iterations ensures that even complex boards with repeated crushing and collapsing are processed correctly. Finally, special attention is given to boundary conditions, ensuring that candies on the edges of the board are checked for potential groups to crush. Here, we start by defining the candy crush function within a class called solution. The input, board, represents the game board as a 2D list. We first calculate the number of rows and columns in the board for easier access later. Next, we define a helper function called mark_for_removal. This function identifies candies that need to be crushed based on whether 3 or more identical candies are aligned horizontally or vertically. To check horizontally, we loop through each row and examine groups of 3 consecutive columns. If all 3 values are the same and non-zero, we add their coordinates to a marked set. Similarly, for vertical checks, we iterate through each column and look at groups of 3 consecutive rows. If we find 3 matching candies vertically, their coordinates are also added to the marked set. The function then returns this marked set containing all the positions of candies that need to be removed. Afterward, we define another helper function called apply_gravity, which will handle the logic for letting the remaining candies fall to fill the empty spaces left after crushing. The apply_gravity function works column by column. For each column, we initialize a pointer, right_row, at the bottommost row. Starting from the bottom of the column and moving upwards, we check if a cell contains a non-zero value. If it does, we move this value to the right_row position and then decrement right_row to shift the pointer upwards. Once all non-zero values have been moved down, the remaining cells above right_row are filled with zeros to simulate the empty spaces. Now, within the main candy crush function, we enter a loop that continues until there are no candies left to crush. In each iteration, we first call mark_for_removal to find the positions of all candies that should be crushed. If no positions are marked, the loop breaks. Otherwise, we set the marked cells to 0 to simulate crushing the candies. Next, we call apply_gravity to let the remaining candies drop into the empty spaces. This process repeats until the board is stable, meaning no further candies can be crushed. Finally, we return the updated board. Here, we begin implementing the Candy Crush algorithm in Java. The method takes a 2D integer array called board as input, representing the game grid. First, we determine the dimensions of the grid, storing the number of rows and columns. Then, we initiate an infinite loop to repeatedly process the board until no further moves can be made. Inside the loop, the first step is to identify any candies that need to be crushed. We initialize a Boolean 2D array called mark to track which cells contain candies to be removed. Additionally, we use a found flag to indicate whether any crushable candies are detected during this iteration. The algorithm starts by checking for horizontal matches. For every row, we iterate through the columns, stopping 2 columns before the end to avoid out-of-bounds errors. If 3 consecutive cells in a row contain the same non-zero value, those cells are marked as true in the marked array, and we set the found flag to true. Similarly, we check for vertical matches by iterating through the rows and stopping 2 rows before the end. If 3 consecutive cells in a column contain the same value, they are marked as crushable. If no candies are marked during this step, meaning no matches are found, the loop breaks, and we return the processed board. Otherwise, we proceed to the next step, crushing the candies. This is done by iterating through the entire grid and setting the value of any marked cell to 0. This effectively removes the candies from the board. Once the candies are crushed, we apply gravity to make the remaining candies fall downward. For each column, we use a right row pointer starting at the bottommost row. We iterate upward through the column, and whenever we encounter a non-zero value, we move it to the right row position and decrement the pointer. This ensures that all non-zero values are shifted to the bottom of the column in their original order. After processing all non-zero values in the column, any remaining rows above the right row position are filled with zeros to represent empty spaces. This completes the gravity step. At this point, the loop restarts, and the entire process is repeated, identifying candies to crush, removing them, and applying gravity. The loop continues until no more matches are found, at which point the final board configuration is returned. This implementation ensures that all crushable candies are processed correctly, and the board settles into a stable state where no further matches can be made. The algorithm is efficient and handles the cascading effects of candy crushes, ensuring that the game logic is implemented accurately. In this example, we start with a simple horizontal match. Looking at the input board, we first identify candies to mark for removal. By scanning each row, we see that in row 0, the values at positions 0, 0, 0, 1, and 0, 2 are all the same, so we mark these positions for removal. Similarly, in row 1, the same pattern occurs at 1, 0, 1, 1, and 1, 2, so these positions are also marked. When we check vertically, no matches are found. After combining these marked positions, we have the set 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. Now, we proceed to crush the candies by setting all marked positions to 0. The resulting board after this step consists entirely of zeros, as all candies have been cleared. After crushing the candies, the next step is to apply gravity. However, since every column is already empty after the crushing step, there are no candies left to drop. As a result, the board remains unchanged, still filled with zeros. This becomes our final output for the first example. Now, we move on to a more complex scenario where both vertical and horizontal matches are present. In this new input board, there are no horizontal matches, but we can observe vertical matches across all 3 columns. To begin, we identify candies for removal. As we scan each row horizontally, we find no matches. However, when we check vertically, we see that column 0 has identical values at positions 0, 0, 1, 0, and 2, 0, so we mark these positions. Similarly, column 1 has a vertical match at 0, 1, 1, 1, and 2, 1, and column 2 matches at 0, 2, 1, 2, and 2, 2. Combining all marked positions, we have the set 0, 0, 1, 0, 2, 0, 0, 1, 1, 1, 2, 1, 0, 2, 1, 2, 2, 2. Next, we crush the candies at all marked positions by setting them to 0. The board is now entirely cleared, containing only zeros. Gravity is then applied, but again, since every column is already empty, no further changes occur. With no candies left to drop, the board remains unchanged after applying gravity. The final output for this example is a board filled entirely with zeros. Now, we move into a scenario that introduces gravity after crushing. In this new input board, while there are no horizontal matches, there are vertical matches in columns 0 and 2, which we will identify and crush in the upcoming steps. We start by scanning for candies to remove. Checking horizontally, we find no matches. Looking vertically, column 0 shows a match at positions 0, 0, 1, 0, and 2, 0, so we mark these. Column 2 also has a match at 0, 2, 1, 2, and 2, 2, so these positions are also marked. Combining them, the marked positions are 0, 0, 1, 0, 2, 0, 0, 2, 1, 2, 2, 2. We then crush these candies by setting the marked positions to 0. After this step, the board shows partial clearing. Column 1 remains unchanged, while columns 0 and 2 are partially emptied. Now, we apply gravity. In column 0, all values drop to the bottom, leaving the top empty. In column 1, there are no changes, as its values are already at the bottom. For column 2, the remaining values also drop to the bottom. After gravity is applied to all columns, the board transforms into its final state. The top row is now entirely empty, while columns 1 and 2 have their candies settled at the bottom. This gives us the final output for this example, which reflects the effect of gravity after crushing in a more realistic scenario. In this problem, the time complexity analysis revolves around the 3 main steps performed inside the while loop, which continues until no more candies can be crushed. First, we have the step of marking candies for removal. Here, the algorithm scans the board to identify horizontal and vertical groups of 3 or more identical candies. For the horizontal check, nested loops iterate over all rows and up to calls 2 columns, resulting in a time complexity of O rows * calls. Similarly, the vertical check covers all columns and up to rows 2 rows, contributing the same time complexity of O rows * calls. Together, marking candies for removal has an overall time complexity of O rows * calls. The second step is crushing candies, where each marked cell is set to 0. In the worst case, all cells are marked, so this step also has a time complexity of O rows * calls. Finally, we have the third step, applying gravity, which we'll analyze next. Applying gravity is done column by column. For each column, the algorithm processes rows from bottom to top, moving non-zero values downward and filling the remaining cells with zeros. In the worst case, every cell in a column will be processed, and since there are calls columns, this results in a total time complexity of O rows * calls. Now, these 3 steps are repeated inside the while loop until no more candies can be crushed. The number of iterations depends on how quickly crushable candies diminish. In the worst case, each pass reduces the number of crushable candies by a constant fraction, such as half, leading to a logarithmic number of iterations with respect to the total number of candies rows * calls. Consequently, the total number of iterations is bounded by O log rows * calls. Combining the time complexities of all steps across all iterations, the overall time complexity becomes O rows * calls log rows * calls. The space complexity of the algorithm is primarily influenced by auxiliary structures and in-place operations. The mark _for_ removal function uses a set to store the coordinates of candies marked for removal. In the worst case, all cells in the board could be marked, requiring O rows * calls space. Since the board is modified directly during the crushing and gravity steps, no additional space is needed for board storage. Furthermore, the algorithm uses iterative loops rather than recursion, so the function call stackspace is constant, O(1). As a result, the overall space complexity is determined by the space required for the marked set, which is O rows * calls. By comparison, a naive brute force approach would repeatedly scan the board and simulate candy crushing without optimizing for marked cells or efficiently applying gravity, leading to higher time complexity and potentially unnecessary space usage. The current approach optimizes the process by marking candies and applying gravity in place, reducing repetitive operations. This optimization ensures that the number of iterations decreases logarithmically, significantly improving time complexity compared to a brute force solution that might require linear passes over the board. In summary, the algorithm achieves a time complexity of O rows * calls log rows * calls and a space complexity of O rows * calls. By efficiently balancing marking, crushing, and gravity simulation, the solution provides a highly optimized way to solve the candy crush problem while minimizing unnecessary operations. One common mistake in the candy crush problem is not handling the cascading effect properly. When you crush candies, the board needs to be updated by shifting all non-zero candies downward to simulate the effect of gravity. Failing to do this correctly can result in incorrect results or even infinite loops. To address this, make sure your implementation simulates the gravity step accurately and repeats the process until no more candies can be crushed. Another mistake is failing to check for all possible crushable groups. While it's easy to detect simple horizontal or vertical groups of 3, more complex patterns like L-shapes or T-shapes can be overlooked. A robust solution requires logic that identifies all valid groups of 3 or more candies, regardless of their orientation. Additionally, inefficiently marking crushable candies can lead to overlapping updates and inconsistent board states. A good practice here is to use a separate data structure, such as a Boolean matrix, to mark candies for removal before modifying the board directly. This ensures that the updates are clear and consistent. Infinite loops during board stabilization are another potential pitfall. If you don't have a mechanism to detect when the board is stable, meaning no more candies can be crushed, your program may enter an endless loop. To avoid this, include a condition to terminate the process when no new groups are found. Another common issue is missing edge cases, such as handling small boards or boards with no crushable candies. For instance, a 1x1 board or a grid already in a stable state might cause your solution to fail if not explicitly accounted for. To address this, it's essential to test your implementation with a diverse range of cases, including minimal inputs and scenarios where no crushing is required. Handling these edge cases ensures your solution is robust and reliable under all conditions. This problem is fundamentally a simulation problem, so success comes from careful step-by-step implementation. A key insight is to break the solution into clear stages, identifying crushable groups, marking them, and updating the board by applying gravity. This structured approach not only simplifies the problem but also makes your solution easier to debug and explain. Additionally, you should recognize patterns that appear in similar problems, such as grid traversal, cascading effects, and stabilization processes. These are common themes in simulation and dynamic programming challenges, and mastering them will help you tackle related problems effectively. While a straightforward brute force solution is often sufficient for small grids, optimized strategies can make your solution more efficient for larger or more complex variations. For instance, union-find techniques can be used to efficiently identify groups in more intricate configurations. Finally, remember that in interviews, it's crucial to articulate your logic clearly. Walk through each step of your solution, identifying groups, applying gravity, and handling edge cases so that your thought process is transparent to the interviewer. Related problems like game of life, rotting oranges, and flood fill also provide excellent practice for similar concepts. When considering alternative approaches, the brute force method is a straightforward option. It's easy to implement but becomes inefficient for larger grids due to repeated scans of the entire board. The time complexity here is roughly O, open parenthesis n times m close parenthesis squared, for an n by m grid. To improve efficiency, you can look at optimized group detection techniques. These approaches use additional data structures to detect and mark crushable groups more efficiently, reducing the number of redundant scans. However, this comes at the cost of increased space complexity. With these optimizations, the time complexity can be reduced to O, n asterisk m, per iteration. For more advanced variations, you might consider using union-find to group candies. This method is especially useful for handling larger or more complex patterns, though it does add some implementation complexity. The time complexity for union-find operations is nearly constant for small groups, making it a powerful tool in certain scenarios. By weighing these trade-offs, you can choose the approach that best fits the specific requirements of the problem you're solving. Great job! Today, we tackled problem number 723, Candy Crush, and explored efficient techniques for solving iterative board simulations. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!